Hi, this is Stephen Brower from Raton Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. And this is meant to be the overview for Irvine Chapter 12, which is going to be on floating point. So everything prior to Chapter 12, we're only dealing with whole numbers, integers, and now we'll take a look at things that can hold decimal points. Woohoo! One of the things that the earlier part of the chapter will do is go over some of the different floating point representations, the IEEE floating point representations that are being used, and then along with that, they'll tie that to the data types that we'll be using. And what I'll point out is that real 4, which is the data type in assembly, and real 8, which is the data type in assembly, correspond to float and double. And since 8 is 2 times 4, that's where the double comes from. But just to try to relate those together. The chapter will look at the register stack. So there are these 8, and they can be referenced individually, but we'll see with the stack of registers that they also can be referenced sort of implicitly or explicitly dealing with the top of the stack. You remember a stack being a stack of items of which access is through the top, and so we can refer to it by or treating it like a stack that way, but we also can individually address the registers. One of the things that will be mentioned is some of the different floating point exceptions that can take place, so things that we have to avoid or detect if they happen. And then one of the ones, so back under the representation and really get down to it, it's a binary representation of a floating point number. But one of the things that, in terms of that representation, is that we can end up with something that's not properly representing a floating point number. So we get not a number, NaN, as being one of the issues that can come out. We'll take a look at the instruction set, and we'll only look at a handful of them in this overview right here. So for loading something onto the top of the stack, FLD, and what I have over here in terms of a simple format, I'm not showing all of it, and I'm not using the same nomenclature or the representation that the book does. So if I say here FLD memreal, meaning that if we have a variable, a real variable, meaning like real 4 or real 8, or well, as an example, real 4 or real 8, that we actually can load that onto the stack. What FILD is for loading an integer. And that's a foreshadow for one of the labs. One of the labs, you'll have to take a quantity, which is an integer, and you'll have to take like a price, which is a floating point. And if you want to figure out the total cost, you're going to have to use FILD to load the integer on the stack, FLD to load the floating point onto the stack, and then you can do an FMUL if you're trying to multiply them out. So FLD is just for loading a floating point number. FILD is for doing an integer. To take what's on top of the stack and then put it in the memory, well, one's a copy and one's a remove, basically a pop. So FSTP, the P means pop, it'll pop the item that's on top of the stack off, meaning it's no longer on top of the stack, and put it into well, the real that we are referring to in memory. An FST will copy what's on top of the stack and copy it in memory, but the value still remains on the stack. And one of the demos that a separate video is going to go through, I actually do a mix of both FST and FSTP. And part of the reason at one point I do an FST is I want a value to remain on the stack for a later calculation we'll perform with it. The FCHS is for changing the sign. It's kind of like the the integer equivalent of NEG for negate. Now here's a handful of arithmetic commands, and in terms of the simple format I'm showing the one where no operands are given. So fadd, well, what fadd does is it takes the two values on top of the stack, adds them together, and leaves on top of the stack the sum of those two. The fsub takes the two items on top of the stack, subtracts one from the other, and then leaves the difference on top of the stack. And fsub and fsub-r have to do whether it's like a minus b or b minus a. Fmul takes the top two things that are on the stack, multiplies them, leaves one thing on the stack, that's the product. Fdiv takes two things on the stack, divides one by the other, leaves the result on the stack. And fdiv-r would be the reverse of that. So if you have a divided by b or b divided by a, you would use one of those or the other. And fabs is for absolute value. And it's for whatever is on there. If it is negative, it makes it positive. If it is positive, well, it just stays positive. So the absolute value. Now, in terms of one of the demos that I have, we'll go through at least some multiplication and some adding. That'll be one of the demos that I have loaded, one of the other videos. One of the things that should be done when you're using something like Java or C or C++, if you're taking to C are two floating point numbers the same, what you really should do is make sure the difference between it is less than an acceptable value. And if it's less than, then you consider it as being equal. And what we mean is, let's say you're trying to find out, does x equal y? Well, what you really should do is subtract one from the other, so x minus y, take the absolute value of it, and then compare to see if the result is less than an epsilon. And if it is less than the epsilon, then they're the same. And so there's a slide that the author has where he steps through loading epsilon, so the FLD for epsilon, and FLD for the two values, the x and the y. So the stack would have epsilon, x and y on it. It would do f sub, and so what we end up with is on top of the stack would be the difference of x and y, below it would be the epsilon. We then do f abs, which then what's on top of the stack was the difference of x, y. Now it's the positive version of it. And then the f com I will compare what's on top of the stack to the thing that's below it, which is the epsilon. With that comparison, if it's above epsilon, then they're not the same. Anyway, so there's a slide. There's a slide that goes through that. The Irvine library. Now, to compare this to integers, we had read dec and write dec for unsigned. We had read int and write int for signed. Well, for floating point, it is signed. There's no unsigned floating point. So there's read float and then there's write float. And what read float will do is, give a blinking cursor to the user. User can type in a decimal number, 3.14, and then hit enter. And then the value the user types in will be left on top of the floating point stack. For displaying a number, whatever's on top of the stack, when we call write float, then it will display that. So one of the demos that I had that's for calculating the tip for a restaurant bill is using the write float. And one of the things you'll see is that it's not pretty. It's coming out in scientific notation. And then the show FPU stack, that would be like the floating point equivalent of dump regs. So dump regs showed a series of registers, and what the FPU stack shows are the values that are in the 8 floating point registers. All right, so that's it for the overview for Irvine, Chapter 12.